Tom will be speaking to us about exploring relativistic laser plasmas with hard X-ray free electron lasers. And he's going to be talking specifically about the status of the Helmholtz International Beamline for extreme fields at European XFELs. So Tom is actually, for many of us, Tom has been a friend of the laboratory for a long time. And actually, he has spent 12 years at Livermore working with many of us in this audience. Tom actually received his bachelor's degree from Caltech and his PhD from Yale. Like I said, he spent 12 years at Livermore. He then moved on to General Atomics. He was a professor of physics at the University of Nevada, Reno. He was director of the Nevada Terawatt facility. And since 2008, I believe you've been in Germany at your current position. I will have to say that just a little side story about Tom. Actually, I knew Tom's family and his wife way before, a little bit before I actually met Tom. So Tom and his wife actually owned a little tea shop in downtown Pleasanton about 30 years ago. And my mother, who used to visit me quite often, became best friends with Tom's wife. And my mom would say, oh, you need to meet Tom. You need to meet this guy, Tom. So we finally did meet. And Tom has, in fact, we became so close that I actually sold him my used Toyota 4Runner. So hopefully you're not mad at me. But so anyway, it's a real pleasure to have Tom here. And Tom, why don't you go ahead and kick us off?
Okay, thanks very much, Frankie. So Marianne and H.O., his stepfather, Marianne, his mother, call him Frankie. So I learned him as Frankie, or met him as Frankie. And the Toyota 4Runner was fabulous because after hours, I used to go out and in the area around Janus, the trailers there, I would spin circles in the muddy when it was winter time or spring. I never got caught, so I guess that was perfectly allowed. Okay, so I'm going to talk a little bit about what we're doing in Germany in the area of high energy density science. Several of you are involved and are members of advisory boards and so on as we develop this. Frankie already mentioned the Helmholtz International Beamline for extreme fields, and what this is, it's a user consortium where several laboratories came together, got independent third-party money from the Helmholtz Association and their other funding agencies, and actually provided the laser infrastructure, both high intensity and high energy laser infrastructures at the European XFEL. So this is very similar to the MEC. We think we're a little bit better. We came second and could improve a little bit on some of the things. And I think some of the success we've had has motivated the MEC upgrade plans. And so it's a healthy competition between Europe and America, which is always very nice. I just want to point out the pointer, I think, is not working for the people online, but these icons kind of show some of the science. I'll get to those a bit later. The image on the right is kind of a summary of my personal interest, which is the relativistic plasmas. And I was here in the good old days of the Nova Petawatt with Scott Wilkes and others, and we discovered the TNSA, the target orientable sheath acceleration, and the filamentation instabilities and all of the structure and the complexity. And I went off in my career and actually worked on applications of laser ion acceleration quite a bit. We learned that there are problems that need to be overcome and that needs the ability to look inside of solid density plasma. And so we had the idea to set up a laser facility at the European XFEL so that we could use new X-ray techniques. This is a case of small angle X-ray scattering to try to look at, for example, the solid density plasma oscillations inside the bulk plasma. I'm having trouble advancing the slide now, I guess. Okay. So this is just a schematic of HIBEF. It's on the HED instrument at the European XFEL, which is on the SASE-2 XFEL beamline. You see that the beam coming in from the lower left, and we've built a laser hutch above a shielded interaction area with commercial high-intensity laser. It's an amplitude technology, about 300 terawatt. It can actually go about 400 terawatts. And then a high rep rate long pulse laser for dynamic compression science. And this is the dipole laser system developed by the Central Laser Facility at STFC. And so from Helmholtz, it's HCDR, my laboratory, Helmholtz Zentrum Dresden-Rosendorf, and DAISY. And we partnered to get significant funding, about 20 million euros. And then the STFC brought in a similar amount for their laser system. And then we've gotten additional contributions from CNRS in France and Los Alamos. And so with fully loaded, and we've gotten a commitment from my laboratory and DAISY, HDR and DAISY, to provide the operations costs over the next 10 years. So in total, this is over a 100 million euro full cost project for about 10 years of operation. Can you click forward, please? The lasers, as I mentioned, were provided by HCDR and CLF. And then a second interaction area is provided by DAISY, including an AGIP detector, which is a high rep rate detector, and a diamond cell system, so one can actually look at the evolution of pressure-driven states. And then HCDR, we have a high field magnet laboratory, and we'll be providing pulse magnets also in about a year. You do the next. You see here just the sketch of the second interaction area. Again, please. Sorry, I already mentioned the additional instrumentation from Los Alamos and CNRS. So that's a visor system, a Xanis spectrometer, and some polarimetry. Again, please. And then this is just a summary of the main scientific pillars in the HIBEF program. So with the relativistic laser, it's relativistic plasmas, laser ion acceleration, laser solid interactions, high energy density science, also astrophysical plasmas, solar physics, and so on. And also looking at the structure of the QED vacuum, trying to look for strong field physics. With the diamond anvil cells and the dynamic compression laser, it's really high pressure phases. I think this is a graph I stole either from John Eggert or Rip Collins at some point in the past. And we're exploring then at higher pressures, planetary interiors, and also new phases of materials. And with the pulse magnets, it's looking at magnetostructural transitions with X-rays. And so in our high field laboratory, for example, we see metastable states from spin and electronic degrees of freedom, but we don't know what the structure is. And so adding the X-rays will allow us to resolve that. So this is a bit of a summary slide of what my scientific motivation and our overall scientific motivation was for developing HIBEF in the first place. The point of combining XFELs and lasers, we can create and probe extreme environments. And using the XFEL, we can do this very precisely. And so this is something that's complementary to what you can do at laser-only facilities where your backlighters are laser-driven. So we can drive high pressure, temperature, density, magnetic fields, phase transitions, applications in geoplanetary science, new materials, and so on. One of the points here is that you can resolve, hopefully, the gradients in the conditions in the plasma in both space and time, because you can use X-ray scattering techniques coherently to look at nanometer scales and temporally a few femtosecond scales because of the pulse pump probe nature of the XFEL. And our idea is that this can really, we hope, improve laser-only experiments in the future because we'll better understand when you're doing short pulse isochoric heating, equation of state studies, or looking at atomic opacities or something. Perhaps we can unravel and better understand what's going on in a laser-only experiment. So this is really meant to be a platform to also support the development of all short pulse laser and long pulse laser technology and science. Second big area, and this is the main area which took me to Germany, was trying to improve laser ion acceleration and other applications of short pulse lasers and ion acceleration with lasers in particular. And in order to really advance this as a field, one needs a better predictive understanding of what's going on so we can do better target design, better shaping of the input laser, the contrast, and so on and so forth. We work very closely with guys like Scott and Yasuhiko Sentoku and Andreas Kemp for many years on these things. And it's really meant then to be a platform where you can improve the development of your physics models by designing specific experiments to measure some specific process in a dense plasma and try to constrain your models. So this is very important, and this is one of the big reasons why I'm here, that I want to promote this idea that high power lasers at XFEL should be a platform for model development and code validation, and I think that's very important. Finally, I mentioned this a little bit already. There are new physics opportunities. I won't say much about this, but this is an example of trying to look at, excuse me, the optical properties of the vacuum that can become polarized in a very strong external electric field. And this is a pure quantum electrodynamics phenomenon that's been predicted. So the enabling thing here is, again, enabling new HED science via X-ray techniques that are available at an X-ray FEL. And so we use diffraction, small angle scattering, we look at the accelerated particles, we use spectroscopy, we use phase contrast imaging, and a variety of other resonance scattering techniques and so on. And so this is kind of the suite of new types of capabilities that we are trying to bring to HED science. Okay, and so in my talk, I've given you a bit of a motivation and an overview. I want to give you a little bit of a retrospective now, and then talk a little bit more about the relativistic plasma science specifically that we're aiming for at HIBEF, and then some aspects of the commissioning and where we are, for example, for getting the dynamic compression and strong field research online in the next year. So, can you advance, please? I'm happy. So back in August of last year, we had a formal opening ceremony. We had our high-intensity laser, relativistic laser, was commissioned. So we had all the politicians here. This is the new director of my center. It used to be Roland Sauerbrei, if you know him from the laser programs at Jena and Dresden. This is now Sebastian Schmidt, the new director of the Helmholtz Center, Dresden-Rosendorf. And they're ceremonially pushing a target chamber into place, the second target chamber. We had a very nice congratulatory greeting from Donna Strickland, and also kind of a retrospective given by Mike Campbell, discussing from CPA to ultra-intense laser physics and why we built HIBEF. You can still find this live stream. Many of you probably were tuned into that ceremony, but I think it can still be found at this web address. And then we had a symposium with very nice talks by some of the leaders in our group and then in our field. I won't go into for detail. So next slide, please. Just to give you a bit of a sense of the retrospective, these are the slides that Mike Campbell showed. I mean, kind of coming from the discovery of CPA and the Nobel Prize in 2018 to the first petawatt laser ever built. And this was at Livermore, of course. And Mike Perry here, who led the petawatt development, and here shown with Charlie Towns, Nobel laureate for the invention of the laser. And then most recently, a few years ago, Mike, I think, is here with Donna at the Nobel ceremony. And one of the big things was building the Nova petawatt, or doing CPA at scale with the Nova petawatt. So using an arm of the Nova laser, doing the chirp pulse amplification. I mean, this was really massive. And of course, you know, Mike Campbell likes to draw cartoons. And so he liked the idea of, or thought he would honor Einstein with the idea of stimulated emission and bringing that to lasers. Let me go to the next slide, please. And the Nova petawatt experience really initiated this field of ultra high intensity laser matter interaction physics, which is a basis for a lot of the high energy density science. So back in the good old days, these artistic pictures you'll recognize were copywritten by Scott Wilkes, who is our resident PR person at the time. And the original discovery of photonuclear physics, photofusion, positron production, and so on in some of the early shots. And then a bit later, when we realized that really dark spot on our detector film was not electrons, it was actually protons. So if you go back to the early literature, the first paper that really shows that, we misidentified it as electrons, but it later turned out to be protons. And that, of course, opened quite a broad research field. And then, of course, a lot of this was driven by fast ignition fusion research, both with electrons and with protons. So this was kind of the context at the time. Next. I guess this is just to show that high intensity lasers are really taking over the world. Next, please. And one of the new, in the last 10 years or 15 years, kind of high intensity lasers program was developed in Rosendorf. So this is the institute that I co-direct with Ulrich Schramm. In our institute, we have a superconducting linear accelerator, which, by the way, makes really nice positron beams for material science, which harkens back to Building 194 in the old days. You can talk to Phil Stern about that. Coupled into this is we have two big lasers, a TISAF petawatt laser, and then a cryogenic diode pumped laser system. So those we operate on the campus in Rosendorf, and then this was the basis for developing the relaxed laser, the relativistic laser at XFEL, coming from the Dresden team, and then the dipole laser shown here. So this is our laser room at XFEL. And I just wanted to comment, I mean, this is where we kind of learned a bit from the experiences at MEC, where we were active users at that time. And we decided to develop HIBEF really from the beginning as a real laser facility, not just as a laser at an end station, but a real laser facility with enough staff, resources, and so on that we could really maintain it and operate it that way. And so we have a dedicated team. It's about 15 FTEs from HCDR and another 3 from DAISY. Toma Tonsian, who many of you may know, he worked at Texas Petawatt for some years as a deputy director, runs our team. And then the support for the laser system, the short pulse, is coming also largely from our infrastructure in Dresden. CLF, of course, is drawing on the whole, the dipole is drawing on the whole infrastructure of CLF, and then our DAISY colleagues are providing a lot of X-ray detection infrastructure from the Petra 3 synchrotron. So we've really tried to put this together in a very thorough way at the beginning. Next, please. Can you just click? Okay, thanks. It's a bit of a strange structure. There was some concern whether it would really work because we're bringing in from different institutions into one facility. Contractually, HCDR is the responsible manager of the facility, and we have the contract with XFEL, and then everybody else has a subcontract with us. So it's a bit complicated. Tax law in Germany is complicated, and so the exchange of operating the laser in exchange for beam time access and so on in a priority way is a taxable transaction in Germany. So we pay tax on beam time that we use in this system. But the nice thing here is, I mean, in exchange for putting all of this laser infrastructure at XFEL, we own, in principle, the user consortium, about 30% of the beam time. And that is, again, a bit like the petawatt, which was Nova Petawatt, which was an internal thing. And we could do things that were programmatically interesting to us. So we developed this so that really members of the consortium could pursue their strategic milestones and have preference, to make sure that a particular proposal for a graduate student's thesis would get approved and could be scheduled. And again, this was motivated largely by the successful collaboration experiences that we had at the Nova Petawatt. And Scott and Steve Hatchett and others can vouch for the fun times we had back then. Next, please. Okay, so I've said a little bit about that we developed our program in Dresden is about developing laser acceleration for application. I'm not going to show much in this regard. I'm just going to try to say that if you don't know about the Helmholtz Association, it's kind of it's DOE-like and it's multidisciplinary, but it's one of the largest research organizations in Germany. We have about 18 laboratories that are federated into this, and several of the laboratories, 7 of them, are involved in various aspects of advanced research and development on accelerators. And a theme is for us as a program, so this is at a national level, is from laser plasma acceleration to laser plasma accelerators. And Germany likes to engineer things and kind of get things to application. And so that's what we've done. And for the electrons, this is laser wake field acceleration that's run primarily by DAISY. And several of you probably know Wim Leemans from Berkeley. He's now moved to DAISY and is head of the accelerator division, is now running that. The ion acceleration is run by ourselves, my colleague Uli Schramm. And our work is also in the research program for cancer. And we do laser ion acceleration for radiobiology research with the long-term goal of maybe making compact accelerators for cancer therapy, for tumor therapy. This just shows, I mean, one of the things that's really impressive if you're in the laser acceleration field, we've gotten laser proton acceleration now to the level of stable operation that you need to do really application experiments over months. So this was a mouse irradiation experiment published in Nature Physics. The reference is down here, where over several months, roughly 6 months, we were running the laser, week to week, day to day during the weeks with endpoint energies between 40 and 80 MeV with a mean around 60. And that's pretty good for a laser particle acceleration system. These were thin foils, form var, a couple hundred, 300 nanometers thick. And the actual mechanism was close to a relativistic induced transparency mechanism. And in order to actually cope with the remaining jitter here in the endpoint energy, we actually used a portion of the spectrum in around 20 to 30 MeV to select. We transported them with pulsed magnet lenses and shaped that into the dose that was delivered to the radiobiological sample. And so we've done real tumors in mouse models, and it had some actually very nice success. It needs to be repeated. But I don't recommend doing medical applications for the faint of heart. This is a tremendous engineering demand in order to get reproducibility in the acceleration processes, that you can actually do these kind of shot on demand when the mouse is ready, when the biologists are there kind of experiments. One teaser, we've now, our team has gotten to the point where they can actually separate this really nice RIT process on maybe say 50-50 from the other more TNSA-like processes. And so we're now getting, with 50% probability up to about 120 MeV. And this will be presented for the first time at the UQuIL 2022. So this is a teaser, an advertiser for Tim Ziegler's talk, who is a student whose thesis this is. Okay, so that's where we were. Can we click forward, please? And just one last thing to chest beat and say that HCDR, even though we're some obscure thing in the former Dresden, in Dresden, and let's see, Klaus Fuchs was the earlier director of the institute that I now direct, so it's kind of old. It's an interesting cultural situation. Even though we're small and we're out kind of on the fringe, we've had an impact. And just, this is from the MEC upgrade kind of summary slides from Siegfried Glenzer. And I just wanted to note that, the short pulse application here and when the long pulse application were actually both HCDR-led experiments. And that's pretty cool for us small guys. Okay, click forward, please. They were big collaborations with SLAC and so on. So. Okay, I'm running short on time already, which is usual for me. Let's look a little bit at laser plasmas. Let's click forward, please. So I like to show this because this is, again, kind of my view. This is why we did what we did. And those of you who are familiar with high-intensity laser matter interactions, you get extreme conditions, even just shooting on a thin, on a planar foil. You get extreme current densities, 10 to the 13 amps per square centimeter or above, extreme fields, magnetic fields of thousands of Tesla, huge space charge fields of 10 to the 13 or more volts per meter. And for short times, picosecond perhaps, you get to temperatures, maybe they're not thermal, but you get average energies of kilovolt at solid density. So really extreme conditions. And this affects things like filamentation and so on of the hot electron transport, and that the hot electrons end up making the sheath for the TNSA accelerated protons. And so we really wanted to understand that and improve that. So this was the motivation. We developed SAX, small angle X-ray scattering, back several years ago, and demonstrated it at LCLS. These are some very nice papers on the technique. So in the end, the bottom line is you get kind of nanometer scale resolution because you're doing diffractive, coherent X-ray imaging. And you get femtosecond timescales because of the short pump probe approach. And so the types of physics that we're interested in really pinning down and improving our modeling capability for are the ionization dynamics, recombination, heating and resistivity, the hot electron transport, but really how the return current neutralizes and the bulk electrons play the neutralizing a role so that the hot electron can properly or efficiently transport to the rear surface. Filamentation instabilities, hole boring speeds, the electron-ion equilibration, generation of quasi-static fields, and if you have material heterogeneous targets, all of the interface physics that happens here. So it's very rich, very complex. And if we really want to make better laser ion sources or isochoric heating experiments or ultra-fast X-ray sources, we want to, take advantage of a predictive knowledge of what's going on here so that we can make those better and better. Let's see, clicking through, this is a little bit generic. I mean, also in general for HED conditions, we can do isochoric heating with the short pulse laser or with the X-FEL. We go to high pressures with the ramped compression. And this is an example of just, several of the various approaches to isochoric heating. This is the old Prav Patel experiment from the 2003. With ion heating, this is some work we did on conical funnel cone targets with magnetized. What we proposed or hypothesized at the time was strong magnetic fields in the cone wall, which actually inhibited the outward flow with some of the up to 100 kilovolt electrons, for example. Pulse magnetic fields, reduced mass targets, and barry-later interfaces where you have a density jump and therefore a pressure or an electric field that can accelerate ions. And these are all very interesting processes that we can look at and improve, we hope, with the use of the X-FEL. And again, so our goal is to improve our understanding. We can do ultra-fast measurements focused with intense and interesting scattering techniques. Why SAX? Well, small angle scattering is often used for colloidal particles, and kind of the size scale is a few nanometers. And that is about the scale of plasma oscillations in solid. So that's why SAX. Let me go very quickly through these. These are just what happens, if you bore a hole. Well, your X-ray, scattered X-rays actually develop structure. If you have ripple instabilities, they develop whiskers. And already back in 2017 and before, we saw these whiskers very easily at LCLS on the MEC. To prove this and develop it further, we used a very simple kind of grading target to impress already a structure and then look at how it evolves. And the gradings are nice because it's periodic, so you get coherent diffraction into spots. So you see the different grading orders, which are also very bright and easy to resolve. And in this simplified target, this is actually, whoops, wow. Okay, this is actually showing the grading structure when it's cold, this upper picture here, and you see the diffraction orders from a square grading. As the grading kind of melts and evolves, it smooths out and the very high Q components are dropping off. And so then you get the lower spatial frequencies. So this is a generic thing. This is what you always see in SACs. When we looked at the time evolution, it was a bit chaotic and not quite what we expected. And so with this simple model that I just showed you, we expected something that would come up and flatten out. What we really saw was scatter in the data points. So we re-examined the simulations and looked a little bit more closely, and we found that at some times we were getting a little bit of jet phenomena as this structure dissolved and it formed into little jets, and then you have another grading structure forming between the original ones. And this ends up, you get oscillations in the various orders. And so, you know, the effective, this is just a fit of the sigma parameter, the smoothing parameter, but it changes in a predictable way, which is coming. And so we discovered, you know, this kind of jetting phenomenon, which we hadn't seen earlier in our simulations in trying to match the X-ray data. Some of the other things we're interested are, for example, heating physics, ionization dynamics, and the fact that as you ionize, you start forming filamentation because the ionization is providing the return current electron, free electron density to balance the space charge forces for the fast forward going. So we like to see these with Faraday rotation, but also with resonance scattering and also with resonance spectroscopy. This is just a simulation of what you see really with a buried layer target. I'm showing this because later I'll show you some preliminary data from a Livermore experiment during our commissioning run, which was a buried layer target. And you see the expansion and the heating in this case. So, and I like this simulation. It's very, very simple. It's just showing the expansion of a very layered target, the electron density on the left, the electron pressure on the right, so including the electron temperature. And you see a whole host of interesting processes from ionization, filamentation, hole boring, hydrodynamic expansion, interface shocks at these. And so colliding shocks if you make a multi and layered structure and magnetic filaments. So even very, very simple targets under these extreme conditions can themselves become very interesting laboratories for HED phenomena. And so this is something, of course, that we want to exploit in the future. Okay, let me talk a little bit about the commissioning. I'm more or less still in time. Okay, this is the relativistic laser. It's a double CPA TISAF system with very high temporal contrast. It has two cooled main amplifiers, which support good operation up to 5 Hertz at 300 terawatts. We oversized the compressor so to reduce component wear and so that we could maybe even upgrade the intensity a bit in the future. A deformable mirror and adaptive optics, and pretty good synchronization with the X-ray beam. So at XFEL, we have a pulse-to-pulse jitter of about 26 femtoseconds. So from one pulse to the next at our 10 Hertz laser, the timing jitter for the arriving XFEL pulse is about 26 femtoseconds, but we have redundant measurements of the arrival time, And so we can correlate those, and we find that our measurement uncertainty of the arrival time is maybe 13 femtoseconds. So that when we bin our data and sort it, that means that we should have resolutions of 10 to 15 femtoseconds on the arrival time. The laser is pretty stable, and it's working well. The bottom line is our pointing jitter is, of order a micron RMS with a f2 mirror. We had a commissioning experiment at the end of last year. Toma Thompson was the PI, but we had several collaborators, including a group from Livermore, including Andreas and others. The interaction chamber was set up this way. This red was the short pulse laser coming in. Here's the XFEL beam. We used a massive lead wall to shield the downstream detectors, SAX detectors, and so on from all of the hard bremsstrahlung that was being made. We didn't have this problem at MEC because we didn't get to the high intensities. And then also, in order to take the SAX signal off of the direct line of sight through the aperture, we used this cylindrical mirror, so-called SAX mirror, HAPG. And we had HOPG and HAPG von Hamo spectrometers for K alpha and X-ray Thompson scattering. Oops. In terms of the detector performance, here you're actually seeing the detector that images the SAX. You're seeing the projection of the two mirror segments. There's hard bremsstrahlung background on the detector itself, and then these bright spots from the mirror are actually from copper K alpha, which is, we were tuning for copper K alpha because we were going to do some resonant SAX stuff, and so you're seeing actually the reflectivity, not of bremsstrahlung from the target, but from copper K alpha from the target. So if you shoot a titanium target or something that doesn't have lines in this region, this background is much more dim. We got the PCI, the phase contrast imaging, working well. We kind of got the spectroscopy working, but we had a lot of problems still with background. Just a very quick demonstration that we could do SAX and PCI, phase contrast imaging, shown here, SAX shown up here, for some simple wires. And so we were simultaneously seeing on different time scales, the loss of the SAX signal in the pump. So you're seeing the femtosecond dynamics of the heating of the on the nanometer scale, and then you're seeing on the 100 nanometer scale on picoseconds with the PCI. We had a couple of different science attempts. So this was looking at near critical foam targets. I won't go into that. This was just a test of the spectroscopy. This was looking at kind of the physics of the expansion of a wire due to return current when you hit it with the laser somewhere, and then look away from the laser focus to see how that current, if it's driving like a Z-pinch process or surface heating or so on. That was quite successful. AWE fielded an experiment where this was a foam or CH target with a, I believe it was aluminum layer, I can't read it from here, that was short pulse laser heated and then actually drove a nice spherical shock through the system. So this is a good test of the PCI. And this is actually probably the most successful piece. And this was the experiment coming from Livermore. And this was a buried titanium wire, I think 4 microns, in about a 110 micron diameter plastic. And one can see it in SAX at early time. So this little piece, you have to have lover's eyes, and we have to get the guys to stop putting everything on a log scale. But there's a SAX signal here that disappears as the wire starts to expand and heat. And then at later times, you see that also in the phase contrast imaging. And we're in a diffractive range, so it's not like a radiograph with a little bit of resolution. I mean, you really see these diffraction fringes changing. And this was something, let me show, I don't know what the state is, maybe Andreas can comment, but I guess Matthew Oliver, if I go back, you'll see, and Tom White and Mr. Allen from UNR, and then Andreas and TLO and the gang from here. So the question will come to you, what's the status of this? Okay, I'm still on time. This is amazing for me. And yeah, John can tell you that. He's seen enough of my talks. Recently, what we've done in the last few months is we've improved the SAC. We had another set of runs in the first quarter of this year. We've improved the SAC's shielding. We passivated the crystal edges to get rid of some stray reflections and reduce the gap so we can get to lower Q. That was all very nice. We significantly improved the shielding of the von Hamos spectrometers, and we started using the imaging detector and the PCI setup actually as a transmission monitor, so we could see the beam, and because we were frequently doing things on resonance, we could see the absorption, and this is really cool. And so we had a variety of experiments. These were all very short. These were each like 2 days. I know some of the experiments from some of the other users were not accepted by the PRP. They kind of reduced all of the interesting experiments, but in the number of shifts, and in some sense kind of batched a few of the HCDR kind of experiments together as kind of a pseudo commissioning time. And so we were looking for pumping of the K to L transitions if we have highly ionized copper. We tried to see resonant sacs, which is also the same effect that when you open up the L shell and you have a bound-bound transition, if you think about it, that increases the opacity, if you will, right there. That changes, if you will, the atomic form factor and relates then directly into also a coherent scattering signal. Unfortunately, we have not yet identified that in the data. We have showed 2-color operations so that we could look at both oxygen and carbon-like copper on single shots, and we've improved the temporal resolution of the grading expansion, or we tried to. The data is still being analyzed, and we actually did some SACs on near critical density foams in support of the relativistic transparency, but other foam experiments in the future. And this was quite interesting because we see the degradation as a function of time of the foam as it's slowly melting during the pre-pulse of the laser. So that's pretty cool. I'm not going to show you much of anything because most of the data is still being analyzed. But as just one teaser online. So this was some of the data from our, and this was an experiment that was actually led by Ulf Sostrow, where we were pumping the K to L transition, the bound-bound transition. When we have highly ionized copper, you open up the K shell, and so you can then resonantly excite a K electron. You open up the L shell. I said K shell, I misspoke. And so you excite a K to an L, a K electron to the L, and then it re-emits. And it turns out that this is exactly the oxygen-like line energy. It matches where our XFEL energy was. And so as a function of time, we're resonantly fluorescing the copper plasma. The next step then is for the other experiments to look exactly on these shots where we know we're resonantly fluorescing the copper plasma. Do we also have, the coherent scattering, resonant scattering, for example? But this was very nice and worked very well. And what's very interesting here is that order of magnitude estimate. This represents, this is absolutely calibrated. So this represents of order on peak 10% of the XFEL photons being absorbed and re-emitted. And then we also see in the imaging detector downstream a 10% reduction in the overall X-ray transmission. We had problems with jitter, pointing jitter of both the XFEL and the laser a little bit, so things are oscillating around. So I don't know the status of the analysis and whether we actually see an image of the hot copper yet, but this looks very, very promising. And so doing these kind of spectroscopic experiments and resonantly looking at individual charge states in a hot dense plasma looks now very feasible. So we expect to be able to do pump probe evolution of selected charge states, say, for example, in a short pulse laser driven copper plasma. Okay, I am almost on time, so I'm about to the questions, and the last things are just kind of status. Let me skip this. This is kind of strong field physics. This is, we're starting to gear up. Can we do dynamic damage? This is one of our early ideas. Let me show this. The dipole laser, we've had a lot, there's a huge community dying to use a dipole laser. John is certainly one of the leaders in this community. Since 2 years, we've had an improved community-assisted commissioning, and Corona hit, and it was a complete disaster because we could not get the people due to quarantine restrictions from CLF, the experts, to come on site in Hamburg to actually do the recommissioning, and it's a very complicated system. We tried doing some things remotely with limited success, and we had problems with parts and vendor availability. So this really set us back. The good news is the other things, the beam transport, the second harmonic conversion, the visor systems we were able to do. But the laser itself is still under the commissioning. We've gotten a lot of pressure from XFEL management, and so now we have a commissioning plan that has been revised, and our expectation is that by the end of summer we'll have the 70 joules, and we'll at least at 1 hertz, and we'll be in a position to finally do the user-assisted commissioning in the first half, spring of 2023. This is not guaranteed. It depends on, you know, not another wave of COVID. It depends on no major breakdowns from a vendor, but this is where we expect to be. And our greatest apologies to the delays. Another thing that many of you know about or were even involved in was kind of, what is the phase 2? What's the upgrade of HIBEF? You know that a few years ago we had an offer for a kilojoule laser from China, from CAPE. It ended up that for political reasons we're eventually not able to accept that. We still have this very nice program for going to higher pressures, for example, making new states of matter like BC8 diamond as an example. We're going to the interiors, studying the interiors of exoplanets and so on. And there was interest from the German ministry to maybe get our Russian colleagues at XFEL involved in this. But of course, since the recent situation since February, that has also fallen through terribly. So we're kind of on hold. We have submitted a proposal for the development of high rep rate kilojoule class amplifiers, including several of our laboratories in Europe, plus Rochester, for example. We will build the external building for the laser because we still have funding in the original package. And there's a strong interest from the XFEL management to actually compete with the MEC upgrade by participating. So we don't have to come up necessarily with this laser ourselves. It'll be something done on a larger kind of facility scale. But with the situation politically now, it's very unclear when this will happen. So we need to focus in the next few years really to make ultimate use or maximum use of the dipole and the high rep rate and really learn how to do high rep rate compression science. My last slide, or almost last slide, is something that's a very welcome new thing, is that in Helmholtz we have things called Helmholtz Institutes, where we have like a mini national lab center at a university. These are funded at like $5.5 million a year. So Dominic Kraus, who was at Dresden and moved to Rostock, and Ron Redmer are interested in hosting one of these, and so we're putting in a proposal, and we made it through the pre-selection process. And so we're hopeful, we're optimistic that we'll get funded an HE, the first real HED center and university-based center in Germany next year, and this will develop over the next few years. And so if you have an interest in this, please talk to Dominic Kraus. He's the young driver kind of bringing this stuff up. But this is a very exciting thing for us. I want to end just thanking all of the people. This is not all of the people, of course. These are the people sitting in in Schoenefeld at the XFEL, but there include XFEL employees, DAISY employees, and our team from Dresden. These are part of the precision polarimetry team from Jena, HCDR, and DAISY. You know Ulf Sostra, I just want to point him out, and particularly Toma Tansian, who's our lead, who's really running the laser laboratory. So if you know those two guys, you have an in, so feed on them. And then this is kind of our extended team, which now is not just HCDR, it's also with Rostock from the guys not directly in the operations that are supporting the HED science. And this is the STFC dipole development team. I thank you for your attention, and I will just leave this up as my last slide, as this is really the message. You know, building up HIBEF has been 12 years of my life. I didn't think it was going to take so long, but I learned when that Livermore multiplied by pi, it's probably more by pi over 2, so that's a good thing, but it's taken a while. And it's time to refresh this a bit and to see what are the areas where that are still relevant, that are important, what questions in HED science can we try to attack and improve our predictive understanding using HIBEF, using MEC as well. But I think this is a real opportunity, and it's been a great pleasure and very rewarding to work on this for the last few years. So thanks very much.
Thank you very much, Tom. Let's see, we're going to go ahead and take some questions. I will say it's great news. I did not know about the proposal for the HED Center. I think I'm on. There we go. Yeah. That's great news about the proposal for the HED Center at Rostock, the Helmholtz Center, I should say.
Well, it's a Helmholtz Institute, Rostock. So yeah. Helmholtz Institute for HED, HIHED.
So that's really great news. Let's see, what we'll do is we'll take questions. There's questions online, so I'm gonna have to step away into the booth to read those questions, but are there questions from the audience here? And if there are, Tom, could you please repeat for the audience that's online? Any questions from the audience here? Okay. Yes.
Well, in principle,
could you repeat the question?
Oh, sorry. The question was, you know, is it possible to bring in, for example, small pulsar or something or other driver to make an extreme state that then can be probed? The answer is in principle, yes. But it has to go through the review process. It really has to be, you know, vetted with Ulf Sostra and Toma Tansian to make sure that it's feasible and it makes sense, and that's not going to put other equipment at risk. You know, so this is a tremendous investment, and of course, and we've been very, very careful with kind of technical safety. For example, we do not allow ourselves to shoot the relaxed laser, the short pulse laser, when the Egypt detector is in the cave, because we don't know if we're going to damage our €1,000,000 detector. And this is a real pain in the ass, quite frankly, because it means when you're setting up that kind of experiment, you are not able then on the off shifts to quickly do some short pulse laser shots. And so we're very cautious about those kind of things, but we're certainly willing to consider those. I speak for the user consortium, not for the operation. So Ulf Sostra is the responsible individual for anything operational like that.
Yes, John.
Okay, so the question is, what's the highest rep rate we've been able to do with the relaxed laser for a real experiment? In reality, it's been about a shot per minute. Those have been simple targets, foil targets that we are not doing terribly precise alignment. So target alignment it turns out is complicated because you have, particularly when you have, you know, two 45-degree beams, an X-FEL beam and a laser beam. And we are quite a far way away from realizing high rep rate shooting with the sure pulse laser. I mean, that's one of the promises and the dreams for X-FEL. I think it's, for me, we're even considering, there's a call open now. I think proposals are due June 22nd. And for some of the proposals, we're really saying, well, let's, you know, can we do that with just planar foils that take a minimum amount of time for alignment so that we can get the repetition rate up? But that's an excellent question. And so tape targets and things like that are a direction for the future. And I think if they're simple and robust, that would be very good. Our problem has been that we've started a lot of work with these nanostructured targets, you know, kind of for the coherent scattering type stuff. And that gets us, yeah, those are much more difficult to align.
Tom, I know we have 2 comments in the chat, so I'm going to just step away for a quick second. Yeah. Okay. Tom, can you hear me?
Yeah, yes.
Okay. Let's see. From Ming Sheng Wei, great talk, Tom. Any plans to implement gas jet and liquid jet type targets?
Yes, thank you very much for the question. Yes, indeed. And we're very proud of that. So we have worked in a collaboration between Stanford, XFEL, and HCDR on hydrogen jets and also on gas jets and cryogenic jets. That effort is being led by Sebastian Gerda from the XFEL team. I believe, yes, they've already had one test set up. They had some problems with the cleanliness of the gas lines and some clogging of the nozzle, so that has to be redone. But yes, absolutely, we will have gas and cryogenic targets.
Thank you, Tom. I believe this one is from our own Mike Campbell, and he says, Charlie T was amazed at the Nova petawatt. He said he never imagined that a petawatt laser was possible. Great memory.
Yes, it was.
And so, and then I think we have one from Axel Hubel. Congratulations on the 120 MeV. What a teaser.
I'm trying to think if Axel is on that paper or not. Axel will have to tell. So Axel was very long at our laboratory. He's now at Berkeley. He was instrumental in the development of our code Pick on GPU, which was our big code, you know, trying to develop HED physics capabilities on massively parallel so that we could scale up from what we were doing with Pickles, for example. That was Sentoku and Kemp's code. And yeah, it's a good teaser. So if he doesn't know about it, that means he's probably not an author. And so they've been holding it tight to their chest.